So our solution, which is via a Moore-Penrose pseudo-inverse, contains this matrix here. So in particular, it contains the inverse of this matrix. So if we want a solution to exist, we want a unique solution, then we need this matrix to be invertible. And what does that require? That requires our design matrix to have full rank. That means, or column rank to be precise, that means the columns, and there are p of them, of the design matrix are linearly independent. So what does this require? Well, this requires first and foremost, as a minimum requirement, that the number of data points is greater than or equal to the number of features or the number of basis functions. I'm using those two interchangeably. So why do we need this condition? Well, first of all, this matrix is a square matrix. It's P by P. Why is that? Well, if we look at phi itself is the vector psi at x1, psi at x2, and so on, down to psi at xn. So what size is it going to be? It's going to be, well, n this way, little n this way, and p this way. There are p basis vectors. So it's n by p. So phi transpose is going to be p by n. And we're multiplying that by phi. So that's times n by p. And these inner dimensions will kill each other. And so we end up with a p by p matrix, a square matrix. And what do we need for a square matrix to be invertible? Well, first of all, only a square matrix can have an inverse. We need it to be positive definite. That's one way we can ensure, it's an equivalent way of ensuring that a matrix is invertible. And what is the definition of positive definite? It's this condition here, that for any vector v that is not the zero vector, v transpose times our matrix that we want to be positive definite. So we want this to be positive definite, times v is greater than 0. Now, if I replace this with greater than or equal to 0, it becomes positive semi-definite. If I replace it with less than 0, it becomes negative definite. Less than or equal to 0, it becomes negative semi-definite. So this has to be true for any, well, what is this going to act on? Since this is p by p, it's going to act on vectors in Rp, key vectors or vectors in a Euclidean space of dimension p. So this has to be true for all v not equal to the 0 vector. And if this is true, then we know that this matrix is positive definite, and therefore we know it's invertible. Watch the linear algebra videos on the relationships between all of these things, and also the kernel and the eigenvalues of the matrix. Now, if phi has full column rank, then its kernel, which is those sets of vectors that it sends to 0, the 0 vector, is only the 0 vector. So we can write like this. We would write the kernel of a matrix, kernel of phi transpose phi is equal to the 0 vector. So there's only one vector that it sends to 0 in this set. Sorry, not this. Phi. There's only one vector that phi sends to 0, and that's the 0 vector. And that is the condition we require for invertibility, or equivalent to invertibility, that the kernel is the trivial subspace of only the 0 vector. So kernel, if you watch the linear algebra videos, is a way of characterizing loss of invertibility, loss of injectivity to be precise, which is why we lose invertibility in that case. Now we can fulfill the required condition. If this has full column rank, which is what I'm saying is the condition that we require, the design matrix, then this is 0 if and only if the v is the 0 vector. So let's now see what this quantity looks like, this quadratic form. V transpose times our matrix times V. Well, what is this? We can write this as phi v transpose times itself, phi v. So we've got the dot product of this vector, which results from the design matrix acting on a vector v. That will give us a vector, and we take the dot product of that with itself, right? Because this, remember, to get this, we swap them around. So then we put the v first, we transpose it, and we put phi and we transpose that, and it's multiplied by this, right? Which is precisely our quadratic form here. And this is the norm, the 2 norm, the standard norm of phi v squared. So that's what I have here. And that's greater than 0, guaranteed, for all v which are not 0. Why? Because the only way that this is 0, phi v, the only way that this is 0 from here, from the fact that phi has column rank, is if this is 0, if and only if v equals 0. So we get this condition that this is greater than 0 for all v except the 0 vector. And therefore, this is positive definite, and therefore it's invertible. Meaning phi transpose phi minus 1 exists. Right? So this is why we require this condition that the design matrix has full column rank. Now I'll come back to this later on, some technical details associated with it.